Let me start with my presentation on the case study of reclamation and ground improvement at JNPT. And this is the largest reclamation and ground improvement work in our country. So I'll just brief about put the outline of the project, how my presentation. The initial start with the project summary, how the details about the design criteria and geotechnical data, then PVD. Ground improvement and reclamation project. So, and then what is the learning about it? So let's go with this. Can we do this? How this? Yeah. Next, please. Is it right? Yeah. Yeah. It's not going. Yeah, because it can't going. Yes. Should I use this one? I can use this. It's working. It's working. Okay, fine. So many of people you know what is JNPT. JNPT is in extended portion of Mumbai. It is in Navi Mumbai. It is comes under Viger. And Jawaharlal Nehru Port Trust. It was developed in soft soil in 1980s, and there is a lot of expansions was done. So this particular case is an expansion of fourth container terminal at JNPT by Port of Singapore Authority. Brief about this project is almost which is around 11 kilometers of edges perimeter bund. Okay. And the depth varies of the soft clay is 10 to around 4 to 24, but majorly it is 10 to 22 in that range, majorly. The consistency it is very, very soft soil, extremely soft. Wait. Okay. Fine. Sorry. The basic data of design is this profile was like this. This front portion will be having a slope with rock revetment. This will have seaside and it will be reclaimed. The bed level was around 0 to maybe 0.5, and then final finish level was +7. So this portion, and the depth of this marine clay was around 20 meters, say 15-20 meters on generally. So this is the basic configuration, and our one thing we need to mention here about the water levels, because as it is we are working in sea, the water level is always fluctuating. So every 6 hours, and low tide will come, and then again high tide will come. So that's another additional challenges for many time it will come. So the water variation was almost 4 meters. So the low tide water will be like this, and high tide water will be almost close to this line, which is around 5. So whenever we'll do the reclamation, later we'll just see the challenges of the methodology of reclamation. That will create another problem of this. The area, the improvement, what is the design parameters? The container yards are for 525 meters per 550 kPa, and the road and rail is having 30 kPa, and all the car parkings, there is 2 buildings was there. The buildings are in pipe foundation. The parking area was open for like tubular loads. The ground improvement is to be done for the car parking, which is 20 kPa. And seismic condition, the 50% of the service floors are considered. This is a seismic zone 4, and design life is 50 years of entire reclamation. So what is the other design criteria? We have the ground improvement is to be done for 95% of degree of consolidation, and the residual settlements after 2 years is 100 millimeter, 5 years is 150, and after 20 years 300 millimeter. That is a maximum limit. And the differential settlement should not be more than 1:100. This is a ground improvement criteria. And what are the perimeter bonds was there? The perimeter bonds, the stability is very essential, very critical point at that location. So the criteria of safety, safety criteria, and the temporary condition it was 1.3, and permanent condition seismic is 1.1, and static was 1.5. This is entire project. We have, based on various loading consideration and clay thicknesses, we have divided into 11 zones. How the zones is been divided is basically with the service loads and the clay thickness. You can see here, I have plotted only the container port or container area, which is most deepest thickness, as well as the loads also high. Therefore, and that this side is road, access road, which I have not put it because of the length. One thing you can see here, all the lines, whatever you are seeing, this is the thickness of the clay. We got this idea from the bathymetry. Whenever we put the bathymetry, we put a contour lines. So why not we can put the clay thickness also similar line, which will give us something good visualizing where the clay thickness is placed. And this the contour of entire project. This is such a large project, you should put like a contour of the thicknesses. So you can get the potential risk and the designs how to be taken, which is more critical and which is less critical. So here this is zone 3. Here I have marked it. What are the clay thickness ranges of the is say for an example of 5, which is deepest side. This, as you know, if you have any time people have visited JNPT, this side is the existing container side, existing JNPT terminals, and this opposite side, this side will be having the elephant cave. So hill side is this side. So as you go away from hill, this is seaside, your thicknesses are increasing. So that's why you can see the zone 3 is having thickness is less, and as zone 5 thicknesses are more. So if you go deep to the sea, the thickness of the clay is increasing. So what are the things we have done? The test, the geotechnical, we have massive number of geotechnical tests we carried out to understand the geological strata of particular condition. So we have done almost 100 boreholes, SPT, with SPT, vane shear test, and other things. UDS samples. The SPT was not much useful in particular case because it's soft soils. It is more about the terminating the boreholes, where it is terminated. Once you get a good strata, you are terminating the boreholes, because our area of interest is the thickness of the soft soil, compressible layer. So that identifying that soft soil, we have done the test on the vane shear test, and we have taken the UDS sample for more possible. Apart from conventional borehole, we have done CPTu test with pore pressure measurement. The 5 CPTs we have done, and also the dissipation test, which is not very commonly used with this, but many of things soft soils we should use, and it is very good test. But how it is determined? It is pushing the rod, and once it is reached the level, whatever the desired level you want to do it, you hold it. And it is having the facility to measure the pore pressure. So you are initially when you are putting, it is measuring the pore pressure, and if you are holding for some time, pore pressure automatically dissipates. So once pore pressure dissipates, you are getting the time versus situations. So from there you can calculate what is the horizontal coefficient of consolidation at field. Because many times we are doing this test to maybe lab, but that tests are having possible damage or disturbance of the samples. So this is very, very soft soil. Apart from this field test, we have done a laboratory test, which is grain size analysis, utterback limits, consolidation test, CU and CD test, one-dimensional consolidation test, which is primary and as well as the secondary, because the total thickness, what are the total settlements are there, that includes the primary settlement as well as. And then consolidation test of these undisturbed samples for calculating the CH value. How we have done this test? This test we have taken the samples, the undisturbed samples, and try to simulate the PVDs in that way. The samples versus PVD diameter, we put grains with the sand rays. And with the sand rays, we have done the test consolidation. So it is allowing the horizontal drainage. So whatever the settlements are happening, top bottom we are shielding it. We are not allowing any drainage to happen in top and bottom. So whatever the drainage is happening, it is happening to the drain only. So with the help of this, we are calculating what is the horizontal coefficient of consolidation with the levels. This is a typical profile of this area, particular project, where this blue is the marine clay, followed by a dense sand layer. Somewhere is available, somewhere not available. Then followed by weathered rock, and our low tide level is close to 0, and high tide level is 4. So water is fluctuating between 0 to 4, 4.5. So sometime in 2 times it will be totally exposed, the grounds, which we generally call as intertidal zone, and then after 6 hours it will have the water. So basically these geotechnical parameters we are putting up the summary of this. So utterback limits and moisture content we have used. If you see this, the liquid limits are almost close to 100. It's more than 100, some is 80 to 110, and moisture content 60 to 80% up to minus 15. Chart datum. Those are not very familiar with marine. They used to call it a chart datum. Chart datum is a thing which is measurement is done from a port level. So port has decided a benchmark there, which is a 0, this chart datum. So all the levels, all the things which are supposed to measure it from the chart datum, because all the dimensions, everything will get it from the chart datum. So that's a marine. It is very common. Otherwise, people just put it RA or something in general. So with it. The you can see here the one very interesting. The NMC is very close to liquid limit, which shows the soil is so soft. It is like water. So liquid limit once it is very close to liquid limit, it's almost like water. Here SPTN value, depth versus SPTN value, as expected, is almost 0 everywhere, almost depth up to -15, and then we are getting some values. Okay. You can see some discrete values are very high. That's value actually is not high. If you see, our entire range was the depth value was varying from almost 4 meter, because which is close to your yield, and then goes to 20 meter. So these are the boreholes where the depth is less. So this is showing that borehole is terminating. The clay depth is up to this much. This borehole is showing the borehole. It is just summarizing the entire project data. So that's why these discrete values are high. It is not the clay. It is just terminating borehole, which is this showing sand level at that borehole. And here you are seeing the CPT data with it, CPT versus depth, as well as the boreholes. Some of the boreholes we have, these boreholes are these dots, rectangular dots, blue dots, whatever you are seeing. These are the field share data. So it is which is almost close to your in situ CPT data. But this rate data, you can see this is not exactly, it is for much below. Why? Because this rate data is also wind shear data, but these are the lab wind shear data. I put it in that list. Because whenever you are taking the samples in this kind of very soft, you have taken the samples and do the extract that samples from the UDS and carried out the lab test wind shear, and it is further remodeling. So it is the strength is much lower than what is actually in field. So these kind of soil, we should not carry out lab wind shear data, which is under predicting the values. This black line we have drawn as a design line for the stability calculation of slope stability for particular this challenge. And this red, another one interesting point was there about this red line is a line we decided about the value of 7 kPa. 7 kPa value is, we have, whatever the ground improvement you are doing, you cannot improve the ground such any value to everywhere, anywhere. Says if it is very soft, very weak soil, you cannot improve up to 50 kPa. 7 kPa cannot be improved to 50 kPa. So we have calculated such a like what is our target share is 50 kPa, particularly soil. So we cannot improve a soil, very weak soil, up to 50 kPa. So maybe 10 kPa can be 50 kPa, but wherever it is 5 kPa, 6 kPa, 2 kPa, soil cannot improve so high. So we decided, we have calculated and came up with a threshold value is 7 kPa, which cannot be less than that value cannot be improved and reached up to the desired strength. And we decided wherever this depth is coming, we remove this soil and fill up with a more, especially at the perimeter bund where the stability is concerned. Other than is okay. This is the value of compression ratio, which is CCY1 plus E0. You can see up to it is varies from 0.25 to 0.18. At the top it is more, and as we go down it is less. Its values are horizontal consolidation ratios are 1.9 to 4 in that range. Dissipation test 0.3 to 4. 3.4 to 4.8, and CH by CV around 2 to 2.5. So with this geotechnical investigation, we have decided this will be done with PVD. So many of the people you are familiar with PVD, but some of them may not be. Just for brief idea about what PVD used to do. PVD is a vertical drains which is allowing more drainage. So when the thickness are very high, like 15-20 meter, and if you have two-edge drainage also, then the soil has to travel, the water has to travel 7.5 meters, if you take middle also, 15 by 2. But that will take long time. So increasing the path and reducing the rate of time we have to use the PVD. So that is a consideration of the concept of the PVD. And in these other sides, you can see the PVD rig, which some people were saying is an excavator with this feature, which used to put it, these rigs and this whatever top you are seeing, this is a PVD, is gone down and slightly it's exposed. This top is the drainage blanket, the partially placed, say this is drainage blanket is 400 millimeter. We put 200 millimeter, put this PVD, and then again we put top 200 millimeter and cover this top portion of what is the exposed portion is there. So it is allowing the water to come and drain through the drainage layer. This is a design concept. Many of you are knowing how the design concept is about the drainage. It is a two-way, both the horizontal drainage and the vertical drainage. But particularly this case, horizontal drainage is a major part. And another things we want to just highlight it here about the smear concept of it. There is having a smear whenever you have installation of the drains, it will create the disturbance zone because of the mineral is pushing through this soft ground, it will disturb. That will call disruption or smear zone. This is a PVD material. PVD material which we have a inner core, which is PVC, and or have filter jacket, which is a non-oven geotextiles. This is allowing water. This is resisting the fines to go inside and block this one. If in case this filter is not there, then fines will go and choke this corrugated inner core. So that's why this is protecting the fines to go inside. So that's the purpose of this. And PVD has a lot of advantages compared to other methods, like it is very faster, it is quality products compared to the sand drains. It has an inbuilt factory quality, it has a faster method, and drainage are much better. So this nowadays, that's why it's very popular compared to any other methods like the sand drains or sand twigs. This is the basic some testing methodology. What are the PVDs needs to be checked? What are the tests has to be done? And this is one things will happen. You need to see this is the drains. What is as installed, and after settlement, the drains will be like this. So somebody has to be minded that whenever we do the test and other things, when the drains will be cleaned, this discharge needs to be taken care at that time, because the state portion discharge anyway it will be very high, but whenever it will be after settlement or during settlement, it will have a kink. So that kink portion needs to be taken care. This is the installation sequence of PVD. First, we put the rig, then we put the mandrel, go down. Mandrel inside will have the PVD with the bottom anchor plate or anchor rod. So once go down, we'll cut the PVD at the top and we'll take it out. This is the overall sequence. This is a particular PVD installation sequence. This is overall sequence. First we put the first layer of the drainage blanket, install the PVDs, and we put a separation geotextile. We put a second layer of drainage blanket, which I have not shown. Then a separation geotextile. Then we put the top surcharge. Why the separation geotextile? It is the top surcharge may not be very quality, very wide range of material based on local available, because it's more about the preloading structure. That's what its main purpose. So if it has a lot of fines, these fines will go inside the drainage blanket or sand blanket. It will choke you. So avoid that choking. We put a separation geotextile. So there is no fines will go inside the sand blanket or drainage blanket. So with this, water will come and it will dissipate. One of the photographs were showing this installation of PVD. This is the installation of PVD I explained. This is the drainage blanket and first layer, and this is the separation geotextile. This is black color. And over this, these fillings are going on. And these are all the instrumentation, settlement plates and other things with the verification. This is very important point when you do the large declavation, because on the PVD is the one part and the reclamation comes is another part, because this particular project we have handled around 1.2 crore cubic meter of material. It is massive. So we need a lot of thinking, we have to put it at that time, how we will put it. So during the scheme monitoring or preparing, we have done a lot of exercises. So we are sharing with it. So we have done a lot of options how to do this kind of 1.2 crore cubic meter of material. How to get it, where we get it, what is the timeline, project timeline, how will we get it, what is the design sequence with it. So first option we work out with the reclamation with the drain sand. It is not available in Bombay, but we thought we have explored these options, maybe which is nearest any port is at the time dredging is going on. So generally port used to do a lot of maintenance dredging, and that dredged material will be dumped in deep sea. So instead of dumping deep sea, we can tie up with them and bring it here and put it. It is a mutual benefit for both the agency, and it will have a very sustainable solution in case if we put it. So that's what we thought of, but this leads a different challenge. I'm putting it in next slides. What are the different issues? And second option, land-based filling, which is available in the Moram called in our local language in Raigar, JNPT area. It's transported through the land tracks and dumped on end-on methods. Yes, the PVD in marine condition, which we have done earlier. Marine condition in 90s, we have done at Kakinada. This photograph from that. We thought of that concept. So we'll do the first marine PVD and followed by a drainage layer underwater. And layer wise, we can feel the up to top of the water, which is 5 meters around. So we can put a layer wise filling. So what will happen with this advantage? It can the subsoil will not get a immediate load of 5-6 meters. We can put a layer wise filling. We step once. We can give a weight. We can put a PVD. We can put 2 meters and then wait some time. We can put another 2 meters. We can wait for 1 meter. But whenever we wait, what will happen? So any the tide will come. Say 2 meters we fill. Your tide height is 5 meters. So what will happen? Your whole material will wash out. So you have to put such a material that will not wash. Water will wash out, but sand may not. Rock may not. So if you put a rock material, so if you put rock, it will not wash out, but you cannot do the PVD. So you are doing the PVD first. That's why. So initially you have to do the PVD, and then only you put the rock layer, maybe 1 layer or 2 layers. You put the rock, and then you put the sand. Then you put followed by once you come above water, you can put the moon. So there are a couple of options we have worked out. But in same option 3 is not very common, because we do marine, and doing marine PVD is difficult, especially this area further intertidal zone, because you will get only 6 hours water, and then this 6 hours, after 6 hours,
Keep pushing this country. This shape.
Is it? Okay. Mud wave and its removal. Mud wave is basically whenever very soft soil are there. Okay. So when you put soft soil outside of 5 meter, this soil is, if you are seeing this 5 kPa, 10 kPa soil, it cannot take what a 5 meter load. 5 meter loads is coming how much? At minimum in the saturated condition, it will come around 50 kPa. It never will take 50 kPa load in 5 kPa. If you take the bearing capacity also, 5 into 5 is 25 kPa is the ultimate it's bearing capacity. If you take in that way. So it never will take. So what will happen? It will the top side which is not good, it will move out of this space because it will have a failure, it will have a collapse, and it will move away. So that will create a model. That model portion it will go out. So this will be very high in terms of our filling of option 2 because we are at a time we are dumping 5 meter because that is only choice. We are directly filling from land. You are end tipping. You are going end and you are tipping, and gradually you are creating the land like that. So that's why it is a high. The extra filling also very high because you are doing the first stage filling very from the top. Project timeline, the marine condition always is tidal dependent, and that's why it is high. Material availability, this option 2 is of course easy because that is nearly available. It's within 30-40 kilometers available. And for option 1, it is almost nearest port is Jaigarh. So which is around 300 kilometers. And option 3 is partly we have to depend on this either Jaigarh or nearby Mumbai. So with all this low, high, and other risk assessment, we finally decided we should go with option 2. So that is only fulfilling the requirement of the project. Otherwise, we will not able to meet the project requirement. So once we decided, this is the sequence. We put it first stage was stage 1 filling with Muram, which is above just above. We want to come out above what, which is 5 meter plus 5 level. We have to come. Then installation of PVD, then drainage blanket, separation geotextile, and then it comes with intermediate pause periods at the edges to keep the stability perfectly. So we put intermediate pause periods, then wherever the geotextile required, inside geotextile, we put the tensile geotextiles, then wait some time, then again we put another layer, then we put wait for some time, then we put another layer. I have a sketch next year. So this is first we put PVD, then we put this yellow line, yellow portion you are filling. Sorry, first yellow portion you are filling, then PVD you are doing, then you put in drainage blanket, then separation geotextile, then stage 2, then wait for some time, then stage 3. So that's a way gradually we are filling at the edge to have the factor of safety in line. And each stages we are checking what is the degree of conservation, because once this stage is happened, the stage 1, before going to stage 2, we should have the adequate strength that stage 2 load it can take. But how do you know that it will take? It is taking with a 2 ways. One is that we have to monitor the instrumentation data, which will give us the degree of concentration, and from the degree of concentration, lot theories and other things are there where you can get the gaining strength, and from gaining strength you can calculate what is the and at that time the gain in strength achieved. And another option, another things are there. You do a borehole and verify physically what the strength is. So we did both. We have checked the degree of concentration, and we have checked the each stage before going to next stage. We have calculated we have determined what is the actual strength. This is the stability calculation. We put it. We have done with the slope W software all the stability calculation in each and every stage with the what are the each area, what are the consideration was there, and the circular, non-circular slip circles has been established, analyzed, and with this calculation and what are the we are gaining? We are gaining what we are getting here. How much extent of extra fields are required to ensure the stability? Because whatever the bonds are there, you have to have extra width. If you see my earlier section, your final rock band will be like this. But what we are doing, we are improving up to this. This is extra field. Because until this toe portion is not improved, your slip circle will pass like this. You'll never get it. If you think only you will be up to the toe, if you improve, then you are not able to achieve the factor of safety. So these extra fields we are getting the number of stages, because as soil is very soft, you may have to increase the stages, but as you increase the stages, your project line will go down. Your timeline, there will be a timeline and project time should be go. It will take more longer time. So we have to ensure both. So for that, many of the cases we use the tensile geotextiles here. It will improve the factor of safety and the stability. And then PVD spacings, we have decided at the 1 meter, which is most optimum. This is each stages one just typical product snapshots of slope stability, particular one critical cases we have put it here. So this is a temporary condition. First stage, just fields are there. We don't have any PVD. What is the factor of safety? This front you are saying is a dredge. This portion is the capital digging. This is minus 16. So 16 meter depth has been dredged in this area. So after dredging, this intervention is there. This is the next stage when the PVD is done, and you are putting the up to second stage. So what are the factors? 1.5 we are getting. Then class 12, this is the maximum level. This is the highest, the top of the structures. And at that time of what are the factors of safety? Then once we improve in hour, the time we have waited of all and improvement is hour, then we are getting factor of safety 1.7, which is more than 1.5. And the same condition we have analyzed for you can see the reduced load of 50% load and the seismic additional seismic loads, how much it is. So it is slightly more than 1.1. This was the parameters we have done for each stages. What was our design requirement? This is the minimum requirement we have carried out in each stages. So before going to next stage, our strength supposed to be this, and then blue for third stage, and then final is after ground improvement this right. So we have determined, and this every stages we have monitored it for the strength, your gaining strength with help of degree of consideration with this classical theory, as well as the borehole for each and every stage. This is a photograph of this showing the instrumentation. This is the vibrating bar piezometer, the black one lines, and this is the settlement marker. So this comes to instrumentation. Instrumentation, we have particular this project. We have used 4 types of instruments. Settlement plates, which is monitored to settlement, which is giving the physical settlement. The next is vibrating bar piezometers or standby piezometers, which is giving us the dissipation of excess pore water pressure. So it is showing that what is the pore water pressure, and gradually with the help of time, it is showing what is the dissipation in this way. Third is magnetic extensiometer. This is some kind of new, or you can say this is the first time we have used there. This is a extensiometer pipe. It has been installed, and this is called spider. So the spider has been placed at that level. it can put any level. So if you put this one, the spider will go down. When the settlement is happening, the spider can slide and it will go down. So whatever it will go down, it will measure the settlement at that level. Another you put it at middle, it will show up to middle. So if you minus it, you can get what is the thickness, what is the settlement of particular this layer comprehension. And from bottom you can say each layer you can make it individual, which is not possible in settlement plates. Settlement plates you can show what is the top settlements, anything below whatever the total settlement it will show. But layer wise settlement it will not show. So each layer, whatever they desire, you can put this extensiometer and you can put it. Then vibrating wire piezometers. Vibrating wire piezometers, we put it, generally it puts at the middle of the clip. Because that there your pore pressures dissipations will be less. Because at the top and bottom you will have another drainage, which is the vertical drainage, will also help. So critical is the middle. So we need to understand, we have to put in middle. So practically that is putting middle is little bit challenges. So what we did there, this because you do not know what is clear thickness. So how do you know middle? You can know only the theoretical clear thickness, but exactly that location you do not know. What we did that anyway this installation is boring. We did the boring up to down, up to the refusal. And then we know what is the clay depth, then we install that middle. We have taken off. The bottom portion is filled with the sand. So the drainage it will come. So we know what the middle only we will install there. So we are exactly getting the clay thickness divided by 2, we put the middle. And bottom portion will fill in the sand. And the inclinometer. Inclinometer only installed at the edges, which is more important at the edges to see the deformation, how it is happening during construction. The bottom of the inclinometer is founded anchored in the rock, and then it is showing the weakness deformation. This was the typical plan of that project, how the instruments was being installed. It is rough tentatively installed in 25 by 25 grid, 25 meter by 25 meter grid, which is very close. So we have installed almost 1,500 numbers of settlement plates and around 200 vibrating wire piezometers, magnetic 140, inclinometer 120. And you see borehole, the intermediate boreholes, we said that during the construction years, each stages will be the borehole, which is around 220 boreholes we have done with the BST at 1 meter centimeter center. And after improvement, we have done 160 boreholes. So this much massive investigations are carried out to ensure that our ground improvements is done up to the required level. So that is very, very important to see whatever you have designed all of time, but at ground performance may not be always as you designed. That needs to be very, very important. Couple of photographs. Yes, right. Couple of photographs with instrumentation to see. Some people might have not seen, especially the students. This is the settlement marker. It has been barricaded. See how it has been done, barricaded, and these staffs they are putting, and this is the data. This is a auto level. This is auto level, which is shows the levels. Okay. So every alternate day we generally do it. Initial period when the settlements are more. When it is being gradually stabilizing, every week we take the reading. That's how we decided that time. This is a magnetic extensiometer. It has been a 5, the spider, and this is a magnets, which is showing the detecting where the location is. So every day we come and take the in magnetic extensiometer. Say spider 1, 2, 3, 4 is there. So every time we take a reading from the top, how much it is. So once you minus it, you get the settlement, how much is happening from the PP. 0 reading, if you minus it, then you get the settlement. This is field instrumentation with vibrating wire piezometers. So vibrating wire piezometers installed with this wire. Once you detect it, one connected with this data logger, you can show this. What is the excess porosity, what is the total porosity temperature it will show at that location. These both the purpose are same. Standpipe piezometer, it will go the water, it will show the water head, and here it is showing the exact. Water heads also fine, but vibrating wire piezometers are more accurate than water head. But sometimes it is physically it is showing it. So that's one advantage. One physically you see you can see the physical water parameters. So third one is the inclinometer. This is the inclinometer pipe, and this is a inclinometer reading tubes. It will show the how much deflections is happen on next day or every day, what other deflections are happening. This is very important, especially at the edges, where a lot of safety hazards and safety things are there. It will give you a lot of warnings in case of any slight movements are happening. You can take a lot of precautions at once, so you can avoid any damage, especially in life or in equipments. It will be so damage. Yes. So this is a typical load settlement graph. This is the settlement y-axis and x-axis. It is a date, the filling. So green lines is showing the settlement. This is showing the PVDs production, and top you are showing the structures, the elevation of this. The other axis is showing how is the field elevation. With this field elevation, we can understand how much field was done particular that day, and what was the settlements. So this data we have used for interpretation. This is the methods very commonly used in entire industry. This is Ashaka methods, which is an observational methods. It is showing how predicting the total settlements. You can understand what is the degree of conservation, because if you know once you know the total settlement, you know today's settlements. If you divided it, you get the degree of conservation. So that's very simple. And this graph, how it is working, what they are doing, this is putting x-axis, you put yesterday's reading, y-axis is putting today's reading. And draw a 45-degree line. 45 lines means what? Today's reading and yesterday's reading is same. And same, that means that there is no settlements happening. So that is 100%. Once 100% is achieving, that will happen practically. The yesterday's settlement and today's settlement both will be the same. But then, here the important thing is that you have to put all the readings in the same duration, same delta, time frame, time duration should be same. Same. You have put the readings for every day, then every day. If you put every week, then every week. You cannot change it. Once you put yesterday's, and then you after 7 days, then never do that. You have to be uniform. That's it. The duration should be uniform. Depending on the settlements you are taking or you're plotting these graphs. These are typical of vibrating wire piezometer. Again, it is showing the elevations with gradually how this is distributing. This is one point very important. We have to monitor it. This is showing this dissipations. But many times we have misleaded with this information, particular point. Because see, this is very coastal region, and every time the tides comes and down. So once the tides come, your actual water head is essentially changing. Wherever the tide goes, your actual water head is going. But this is not happening in the natural wherever we are doing ground improvement, because water level is almost fixed. Seasonal, there is a change. Okay. That is, but it has a lot of. But here every day 2 times comes, 2 times goes. So that's there. Whenever you are taking the reading, you need to understand whatever the time that is, because. And that's how what we did. We put an observation well, taking the reading, and see the observation how much it is there, and then adjust this level while the interpreting. Otherwise, it may mislead your data. Even though your data is very good, everything, but that's a practical problem. This is a magnetic extensiometer. It is showing what is the thickness of the clay, what is the settlements of the morum. Even morum also has loosely filled as the first 5 meters, which is just done because we cannot compact underwater. It has some settlements. So that's been also we taken care how much settlements are happening at more. This is a graph of extension inclinometer towards edge. This is the seasides, and this is the every day what was the reading of this. And for this, what we did to benchmark it, we put two inclinometer side one behind other. If you see my layout, one we put it the edge and one just put it inside, 50 meter inside, quite inside. So we just check that is the datum to check every day's reading. So with respect to that, how much is movement is happening? And we have created, we have did a analysis in axis and see what is the deformations are happening. So what are the deformations are critical with respect to the safety point of view and project. So we have projected here. Say once it has to have an alert, then action, and then alarm. So suppose this lateral movements is 100 millimeter, it is alerting. So your settlements are deflections are more. So you need to take a action. What are the actions? We have noted down right. So it is showing the stress, so you have to be gradually have to reduce it load, where you have to do some actions. Then you need to put actions. You have to frequently monitor, you have to increase the monitor, you have to change a little bit. And alert, alarm is if it is more than 180, then you have to remove everything because you can allow a structure to fail, but you cannot allow the people to fail, but the life should not go. To make purpose at the end, the life should not go. So this 140, we put it in such a like that this is should be, then you have to vacate the place immediately. So you go that one, let it fail, come up after some time, modify, rectify, but we cannot allow it to structure. So that's why this is the main purpose of putting the instruments are very inclinometers. That's the main purpose. So we have never lost a single people, or we have never faced this issue for a structure or insect damage in that area. Now this is more technical. Back analysis of the instruments, which is the instruments are very likely with this instruments data. See this, what we did, all the instruments, you can see massive number of instruments is done, and all the instruments are, we have back analyzed. Because whatever the instruments, whatever things we are doing, theoretical calculation, it will never match. It can go at any project, it will never. If you have a sense, because ground will perform its own. So what we did, we have calculated theoretically what are the settlements happen, what is the timeline is happen. So days versus, we have calculated days versus settlement theoretical graph, and we have plotted the actual graph. It is not okay. So that is somewhere our assumptions or considerations are different, and such is happening. Okay. So what we did, we have back analyzed all the parameters, especially the influencing parameters, especially the compression ratio, the horizontal considerations, the smear effect, and the smear diameters. So these are the slightly changes we have done, and we have tried to back analyze. Say suppose this red in the dotted line, we have back analyze this one and try to fit this one, this start as much force. So with help of it, we have back analyze these parameters to come up with whatever the shear values, compression ratio, 6 plus 1 plus Vg, and the consideration of CH, and we have presented. So this we have used for the settlement data. Now come to the piezometer data. We have used this piezometer data for distributions. If you look into this theory, this is very classical theory of consolidation by Hans Bohm. This is what is the degree of consolidations happen. Degree of consolidations happen due to the horizontal consolidation. With this, whatever we did, we have taken a consideration there is no vertical consolidations are happening because the clay thickness is 15-20 meter. The vertical consolidation is very major because it has to travel almost 10 meters from the beginning. So consolidation is less. So what we consider, okay, vertical consolidation is not there. So horizontal consolidation is there. We have taken this equation. If you are means you can take it like this. What are the today's pore pressure T delta T today's pore pressure, and what is the original pore pressure delta U earlier That is the ratio. So if you simplify this equation, you come up with a ratio, this log of u0 by ut equal to alpha into t. So it's a linear curve, right? So what we did, y-axis, we plotted this log u0 by ut, and x-axis p. So whatever the curvature, whatever the slope will get it, that is alpha, which is a function of ch. Rest other parameters are fixed. This drain from the drain diameter, drain spacing, we can get d. Fn is basically from the drain ratio and shear ratio. So this is also fixed for everywhere. For particular that entire project it is fixed because the spacing is fixed and other thing. So it is basically a function of ch. With the help of it, we have calculated the ch horizontal consideration. So with the help of this back analysis, we got this are the value. Radial consideration using the lab almost close to 2 to 4 we got it. And then CPT distribution we got it to 2.5 to 5.2. Then back analysis using the field settlement data, we got 3.5 to 3.75 to 4, and with the piezometer data, we got 3.4 to 4.7. These are the which is almost matching. Field is giving us better results. As we said that lab is little bit less. That is quite logical because whenever we put a lab, I said that these samples are so weak, and it is almost impossible that getting an undisturbed sample, and those samples to be taken in the lab and extract those samples and get the same undisturbed layers. It's not possible. So it will have the slide, even whatever the best quality you put it, it will have some disturbance. So that's why it is showing little less value because it's disturbance or visibly effective. At rest, you can see the field values are good. So what are the key learnings and conclusion with it? Our understanding from this project, it's a BAM with an intermediate pulse periods are very essential. You have to check at every stage. Every stage needs to be checked. What are the widths are required? Monitoring of the inclinometer readings with the triple limits needs to be clearly put it. So everybody seriously think and everybody take that one very seriously. Otherwise, it will create a massive damage to the project, life as well as the money. Confirmatory borehole at each stage after pulse period. It is very essential because whatever theoretically you do with the degree of consideration workings, because this degree of considerations workings has some limitations. Because intermediate pulse period, whenever you are putting the degree of consideration not achieved up to 90%. So what is happening if you check with the this Ashoka graph also? This is showing the yesterday's reading, this today's readings. It will be good when the graphs are flat. When the graphs are not flat, it's not stabilized. It will not able to give. So this methodology has a limitations that it is good predicting if the degree of consideration achieve at least 60%. But the initial period will not achieve the 60%. So you will not get exactly degree of consideration from the internal technique. So do the confirmatory borehole at the intermediate, especially wind shear test, which is direct strength test, which is our desire. So do the wind shear test, wind shear, get the value. Once the values are matching with your requirement, design requirement, how much it was, you should go for next stage. Rate of filling. For such a massive project, we say this is very important because so 1 lakh, 1.2 crore, we have to fill say maybe 30 months. So it's not that easy. We have to put a lot of effort, lot of excess, lot of masses we have to put it. So sometimes if you put very rapidly one particular area, it will increase the excess pore water pressure so high. So once excess pore water pressure it will high, it will try to fail the area. So it should be allow also the pore water pressure to dissipate. Once you allow, it is gradually gain. Otherwise, what will happen? Immediately you are putting the load, you are increasing the load, but you are not allowing soil to improve it slightly also. So you cannot, your edge will collapse. So our experience with it that the filling height of a particular area should not be more than 500 millimeter per day. The settlement gauge and extension meters are more reliable than piezometers. And we said this reason of why it is more reliable, because we said that okay, we have the tidal variation is coming in picture, that has an impact. We have done the observation work through this with it, but always may not be possible practically. We have to do the everyday readings every day. Some readings they will take, practically it may not be possible. So that practical considerations, say 140 instruments was there, you have to take the readings, and every readings may take 20 minutes, 30 minutes. So morning you can take the observation while reading, afternoon, but every time you cannot take it. But variations are every 6 hours is 4 meter, 5 meter variations happening. So tidal variation, as I explained. Manufacturing of the instruments and damage and during construction. This is purely construction issue. Is but very, very important issue. You see the large number of reclamations are going on, massive number of cracks are coming, so that may damage your instruments. Once it is damaged, you cannot put a new instrument to get it done, because if you put the new instruments and immediately it's fine, but if you see that one for a long time, for some time, then you will lose some data, which is you don't have any other record to recover those. So we should do more number of instruments. The contingency plan should be there when we go specific to the instruments, especially the settlement place. So at least we have the data. Even though some instruments are not working, okay, we have the additional data. From this additional data, we can correlate. When the large settlements are anticipated, the preloading heights should be considered at all. Why it is? Because whatever the 50 kPa I said, the design load, it is at plus 7. Right. So we do plus 7 and we put 50 kPa is a 3 meter height. Okay. If you take a density of 17. Okay. So 50 kPa at 7 meter, if you put 3 meter, so 10 meter. I can put it up. What is happening after consideration, this 2 meter settlement is anticipated. So the 10 will become now, or will have how much? 8. So what is your left with? You are having only 1 meter, 1 meter blocks is there, above 7. Because you have to have plus 7, above plus 7, otherwise you have to have 55. So what is you should do it? You should anticipate those settlements, calculate the settlements, and top it up initially. So instead of 10, that's why we put 12. So after settlement, you put 10, which is your desire. Then smear and disturbance zone is very important. So this is being taken care because of very soft soil, it may happen. And that's why our suggestion, in particular this JNPT, we should not reduce the PVD spacing below 1 meter. Because we did a particular one case, one particular area trial with 900 millimeter, but it is not having any benefit rather than increasing the massive number of PVD numbers. So 1 meter is the least possible. Offshore collectors, we said are very good, reliable predictive methods, but the degree of conservation is good prediction in case it is achieved at least more than 60%. The sequence of reclamation is very, very careful, especially because of the dredge, deep dredging is there. Particularly this project was having a dredging, water pocket dredging. So before the dredging sequence and the reclamation sequence is very, very important. If you suppose you do the reclamation first, in this case we have dredging you have first you put the reclamation, and then once the structure is there and you start dredging, then the whole thing will collapse. So either you have to do the reclamation first, complete the reclamation, do the ground improvement, all everything over there, then only go for the dredging. It's very possible. Or you can do the dredging first, complete the dredging, and then with the dredging you do the reclamation. So the sequencing of the things are very, very important for particular this kind of job. This is a completed photographs of particular the land. The edge was having the rock revetment, that is for short protection point of view. the wave will come, and that's what. This is the edge where it is. This is a completed view of the project. Particular, this is the. So this is a complete. This is a jetty. This is approach. This is the edge. This is the yard, which was designed for 50 kPa loading, and this is operating since 2017, almost 5 years, 6 years without any settlements, any discussion. This is that the performance is very satisfactory. Thank you.